The figure we see here represents a bar magnet in between the poles of the larger magnet. The larger magnet gives rise to what we're going to consider to be a relatively constant magnetic field B. The red arrows represent the direction and magnitude of B. Constant direction from north to south and constant magnitude. The bar magnet has a north and a south pole. The north pole is repelled from the north pole of the larger magnet and experiences a force F in this direction. We experience a force F in the opposite direction, and really we should call this negative F here, on the south pole of the bar magnet. These two forces result in a torque that tends to turn the bar magnet toward the magnetic field, with the south pole facing the north and the north pole facing the south. Or if we forget about the poles of this magnet, with the north pole repelled by the magnetic field, the south pole attracted by the magnetic field. This torque is going to equal, of course, the torque from this force is going to be equal to the moment arm here times the sine of this angle theta, theta being the angle between the direction of the magnetic field and the axis of the bar magnet. So that we're going to have a distance L over 2 here times sine theta multiplied by the negative F. And that's going to be the torque exerted on the south pole. Similarly, we're going to have a distance L over 2 here times the sine of theta to give us the perpendicular distance and so forth. And then multiplied by this force F, and that's going to give us the torque on this end. So that we have torques negative L over 2 sine theta times F and another negative L over 2 sine theta times F. Now these torques are negative because they both tend to rotate the bar magnet in the clockwise direction, and by convention the clockwise direction is negative. If we add these two equal torques, we see that the total torque is negative L sine theta times F. We note that if we had a stronger magnet, a stronger bar magnet, we'd have a greater F, and if we had a greater magnetic field, we'd have a greater force. So we'd have a greater torque in either of those cases. If theta is 90 degrees, so that the bar magnet would be perpendicular to the magnetic field, that's when we're going to have the greatest moment arm here and the greatest torque resulting from these two forces. Now let's be clear, these forces aren't going to change with angle. The only thing that changes with angle is the sine of the angle itself and the effective moment arm. In any case, this is what we have. Now we note that the torque is proportional to the force, and the force that we get here, the force F, is going to be proportional to the strength of this bar magnet for a given magnetic field here. So that since the torque is proportional to the force, which is proportional to the strength of the bar magnet for a given magnetic field, the torque will be directly proportional to the strength of the bar magnet. For a given length of the bar magnet and a given magnetic field, the torque will be proportional to the strength of the bar magnet. Now let's see what we can do with this. Okay, if we have a magnetic field represented by the red vectors, an angle theta between the bar magnet and the magnetic field, and a north and a south pole, and notice I've got the north and south poles reversed here, that's alright, then I'm going to get a torque, which is, of course, the length of the bar magnet times the force times the sine of theta. But we don't need to know the force. What we need to know is a certain characteristic of the magnet called its magnetic moment, or its dipole moment. Now, the dipole moment is simply something that we multiply by the magnetic field B to get the torque. remember we said a minute ago that the torque was proportional for a given length of the magnet to the force, which in turn is proportional to the strength of the magnet. So that mu is a measure of the strength of the magnetic dipole. Now let me back up and say dipole means that we have a north and a south pole. That's all it means. It means that magnets always come with north and south poles. At least we've never observed a magnet that has just a north pole or just a south pole. Okay, that would be called a monopole, and no monopole has ever been reliably observed. And we have good reason to think that no monopole has ever been observed. So again, this magnetic moment is the quantity that we multiply by the magnetic field and then by the sine of the angle to get the torque.